principle and its application. This circuit is known as Wheatstone circuit. It is a circuit of 4 resistors in the quadrilateral arrangement. And the resistance of the resistors are designated here: R1, R2, R3, R4. The resistance of these resistors are let R1, let it be R1, R2, R3, R4. And to this circuit, the voltage source is applied. EMF, the external EMF is applied across the 2 points, these 2 points, and the remaining 2 points are connected through the galvanometer. G stands for galvanometer. And with this source of voltage applied to this circuit, this source produces the current through the conductor like this. I is the current. So let us see how does the current flow through the circuit. That you understand by using Kirchhoff's first law. There are junctions or the nodes. Let us understand what is the current, how does the current flow and divide at each junction. So at this junction it is a current entering from the source. So these 2 junctions it is leaving. So this current is now divided at this junction into I1 and I2. So now I1 is a current flowing through this conductor, I2 is through this conductor or resistor. So it is division, divided the current into 2 branches, 2 different amounts, I1 and I2. So this current flowing in this direction, when it reaches this junction, now again is that it is arriving, these 2 are leaving. So now at this junction, this current is further divided into as current I3 and current Ig. This current is flowing through this resistor and this current is flowing through galvanometer Ig. Let us call this as current as Ig. And when this current is flowing through this and this current is flowing through this, they reach at this junction and merge into one single current. It is what is that leaving. So this plus this gives us to I4. So amount of current flowing through this conductor is I4, having the resistance R4. And at this junction, these 2 currents are arriving and merge into one current again. Add up and I again back to the circuit. So this is the direction of the current at each junction. It is in accordance with the Kirchhoff's law. Now in this circuit we have 2 loops, that is 2 circular, what is that, closed circuits. This is one loop, A, B, D, A. One more loop, B, C, D, B. There are 2 loops. If there are loops, we can apply the second law of Kirchhoff's. So let us apply Kirchhoff's law to this loop as well as this loop. As you know, there are three conductors. These are conductors, these two resistors. Conductor, conductor, and conductor. Conductor of resistance R1, resistance R2, and the conductor of resistance is Rg. Rg means resistance of the galvanometer through which when the current is flowing, there is also resistance. Let us call this as Rg. So I have to write what is the potential change at this potential change. Sum of them is equal to 0 using sign convention. See that the direction of the current is direction like this, clockwise. That is current direction, loop current direction is this, clockwise in this loop. These two are in the direction of the loop, but look at this current, that is direction of current. It is in the opposite direction. Look here. When you think about this loop, these two are in one direction, this is in the other direction. Therefore, if this takes minus, this will take plus. So, potential change at this, what is V is equal to IR. Potential change, V is the potential change is equal to IR. What is IR? I1, R1. What is this potential change? IR, IG, RG. Minus same direction, but it is opposite direction, that is anti-clockwise, plus. The potential change is high R, I2, R2. Sum is equal to 0. This is second law for this loop. What is the second law for the second loop? The loop is B, C, D, B. And see the loop current direction. This is the loop current direction. This is the direction. This is the direction. This is a clockwise like this. We say this is a clockwise direction like this. But this direction is opposite to the clockwise. So let us write second law means potential change at this conductor and this conductor and this conductor. So what is the potential change? This is the direction of this is a direction like this, clockwise, minus potential is IR, I is IG, R is RG about this conductor, and about this conductor across this, what is the potential change? Minus IR, I4, R4, and this is the opposite direction, therefore it takes plus. The potential change is IR, I3, R3, sum is equal to 0. So we get these two equations from this circuit with this source of potential. These are the two loops. Now there are four resistances are there, R1, R2, R3, R4. We can able to adjust the values of these resistances so that the current flowing through the galvanometer 0, so that no current flows through galvanometer. It is possible to adjust the resistances in this circuit so that no current flows through the galvanometer. If there is no current is flowing through this, that Ig is equal to 0. It is called as balanced position, that is balance of the Wheatstone network. Wheatstone network is balanced. It is balanced, there should not be no current flows. If that is the case, whatever the current here, when the current is flowing like this, it is flowing as it is. Same amount of current flowing, that is I1 and I3 are same. And here also what is that, whatever the amount of current flowing here, same amount of no current is flowing through because no current is flowing through this. So I1 is equal to I3, I2 is equal to I4 at the balancing position. Remember these equations. Ig equals 0, I1 is equal to I3, I2 equals I4. Let us write this into this equation. See that. So these are the equation for balanced disk at the balancing position. For the first equation, let us write this Ig is equal to 0. And see that what is Ig equal to 0 means second term becomes 0. So this plus this is equal to this. One is minus, other is positive. Taking these two on either side of the equations becomes this plus. This is product form. What is the ratio form? Ratio is I2 by I1. If you write this I1 to left hand side, this becomes right hand side. I2 by I1 is equal to R1 by R2. Write this as equation number 3. Similarly, for the equation 2, let us apply all these equations. That is, put Ig equals 0, this becomes 0, and I4 is equal to I2, and I3 is equal to I1. See that what you get? This equation you get. Equation 2 becomes this. Since one is minus and positive, taking another side of the equals. Similarly, we have a product form in the ratio form. That is, I2 by I1 is equal to I2 by I1 is equal to R3 by R1. So compare this equation 3 and 4. The left hand sides are equal. If the left hand sides are equal, right hand sides must be same. Therefore, this R1 by R2 is equal to R3 by R4. So this equation, it is also same as what is that? We can replace R1 by R3. Can you interchange this? R1 cross multiply R1 by R3 is equal to R2 by R4. So this is the principle of Wheatstone principle for this circuit. What is circuit? 4 resistors in the quadrilateral fashion. That means at the balancing position, when there is no current is flowing through this conductor, the ratio of the resistances, what is that? R1 by R2 is exactly equals to the ratio of these two resistances, R3 by R4. This is known as Wheatstone principle, the equation. So, what is the application of this Wheatstone principle? This is about, that is this circuit and the equation. It is known as the principle of Wheatstone network. What is the application of this Wheatstone principle? We can able to construct the bridge like this. It is called as a Wheatstone bridge. Bridge like this. For this circuit, for this fashion of circuit, look at that, same thing is constructed. That is, so it is a metallic strips fixed on a board like this. These are metallic strips, and there are two gaps here, one gap and one more gap. To this gap we can connect, to this gap we can connect the box like this. It is called as resistance box, where there are number of plugs and each plug has its own resistance. The plug can have 20 ohm, 30 ohm, 40 ohm, so on. So resistance boxes with a known resistance values. So it is R1. When you unplug that, it is the resistance of that. R1 is the standard or no resistance we can fix. Or we can, what is that? Connect a conductor of no resistance R1 here with this. In the other gap, we have a conductor, a solid conductor. It is any conductor, a metallic conductor, or a alloy, or anything, or material, whose, what is that, resistance to be determined. Resistance to be determined, very important. Determination of resistance of a conductor. The conductor, that is a specimen conductor or a sample. That is the application. we can able to find out using this principle or using this instrument, we can able to find out the resistance of that conductor. Then you take out about what is that leads to applications, some other application evaluations from that resistance. That is the resistance of this R3. The resistance is not known, is connected like this. That is, the conductor is made into what is that? A wire of what is that? Uniform diameter. Very important. It is made into a wire of uniform diameter. That is a connection. And this metallic strips here now at these two ends, that is a metallic wire is connected like this between these, that is these 2 points of the strips. And these metallic strips are made of thick copper. Metallic strips are made of thick copper because copper is a very good conductor. We need very good conductor for this because a resistance, it should be a very good conductor. And to increase the conductivity, it is made in this shape. It is what is a strip. If you have in a strip shape, because what is that? More area of cross section. Higher the area of cross section, higher is the conductance. That is why to increase the conductivity, it is made in the form of metallic strip, thick copper metal of this kind. And this is a metallic wire. So this is drawn into a very thin wire of uniform diameter. That is a thin wire of uniform diameter, very important. Diameter at any point will be uniform, same diameter all over, into a thin wire. And this wire should have 3 important characteristic properties. What are them? This material should have high resistance, 1 point, and this material should have very low thermal coefficient of resistance. That means the resistance of this wire should not change by a change in temperature due to weather change. When weather changes, temperature changes. The change of temperature will affect the resistance. Therefore, we should have a material of low thermal coefficient of resistance. Very low or low thermal. So the temperature should not affect the resistance of this wire. That is the material we need to use. And one more property, the material should be chemically inert. Chemically inert means should not be reactive, should not undergo any kind of reaction by the action of any components of the atmosphere, because it touches the atmospheric air. You know, as there are number of components are there. Oxygen is there, carbon dioxide, moisture, water, and also some other pollutants. The metal should be chemically inert. Any action on these components leads to chemical reaction is called as corrosion, metallic corrosion. That chemical reaction will change the composition of the material, and change in composition will change the resistance of the material. That should not be there. So it should be chemically inert. For that material, we use these alloys, metallic alloys. So this metal is made of the alloys, any one of the alloy. There are alloys of these characteristics. Here one is manganese, and other alloy is constant nickel chrome alloy. Manganese, constant nickel chrome alloy. This manganese is an alloy containing alloy of copper, manganese and nickel. Manganese is an alloy of copper, mixture of copper, manganese and nickel. This constant is an alloy of copper and nickel. And nickel copper is a alloy of nickel and chrome, nickel chrome. So these are have that kind of property. Therefore this wire is made by this or this or this. So these are the construction, and at these points the voltage source is connected like this, voltage source, and from the midpoint of the strip here galvanometer is connected through the sliding contact, a metallic sliding contact which can slide over the metallic coil like this. It can slide all over the metallic coil. So that is a construction. If you give the contact through the what is that sliding contact on this metal, see that when I switch it on, current flows to the galvanometer. If it is touched at this point, it will be deflected in one direction. The same sliding contact touch at this point, it will be deflected in the other direction, opposite direction. So the current direction changes. So that is what is our indication that current is flowing through this. Now R1 is what is unplugged, it is standard. What is R3? Resistance which we do not know, that is Ru, to be determined. And what is this R2? This length of the conductor is R2, that is this R2 is directly proportional to L, and R4 is directly proportional to 100 minus L. Total length is 100 centimeter or 1 meter. So if you touch here, it is length is L. If the point is L, if you touch it, this length is 100 minus L. If this is 30, 100 minus 30 is 70. If this is 20, 100 minus 20 is 80. That is like that. 100 minus 30. This remaining length is this. So this resistance is directly proportional to it. This resistance is directly proportional to this length. Why? Because this is a material made of same material, uniform diameter, length. Look at this. For any conductor, you can write this equation. Resistance of a conductor is directly proportional to L by A. That is equals specific directly proportional means equals constant. Specific resistance into L divided by A. Length of the conductor divided by area of cross section of the conductor. Length divided by area of cross section. So I said uniform diameter means area of cross section at every point remains same. RS means specific resistance. Specific resistance is specific for a material. If the material remains same, it is same. R by S is constant, the ratio. So equals this constant means R proportional to L. In this case, the resistance is proportional to L. That is, if you take this point, resistance of this portion of the material is proportional to length of this material. And for this point, resistance of this material is proportional to 100 minus L. You can write this. So according to that concept. Now what else you have to find out? Now you can go for experiment. This is a construction. For the experiment, you switch on this and make a sliding curve. What is a slide over here from here? One deflection, and deflection decreases, and some other point here, no deflection in the galvanometer. That is, at some point like this, no current is flowing to the galvanometer. When there is when the galvanometer shows no deflection, no current is flowing to the conductor. There is no current flowing to this. If that is the case, we can apply Wheatstone principle. What is Wheatstone principle? R1 by R2 equals R3 by R4. At the null point, that is, two legs of the bridge are balanced. So at the balancing point, this equation is applicable. It is Wheatstone formula. So now with this equation we can write what is that already M is calculated. R2 is equal to L, R4 is equal to 100 meters. Replace this and this. By this we get this equation. So this is what is that. You unplug some standard points, 20 or 30 like that suitable. That is a value, resistance value, standard value. Known. And it is not known to be determined. This is, it is measured as L here from this point. This is known, measured, remaining. And you can calculate what is Ru, resistance, that is unknown resistance. That is, this value is known and these values are known. Substitute them and simplify, you get Ru. What is Ru? Resistance of a specimen to be determined. Let us say R. Let us call it as R, resistance of the specimen we determined. So now I want to be using this value. We can evaluate specific resistance of the material. We have to understand what is the specific resistance or the specific conductance of the material that we can evaluate. So recall this formula, same formula for any conductor. R proportional to L by A. Therefore, R is equal to Rs into L by A. Specific resistance into L by A. Length of the conductor and diameter of the conductor. What is the specific conductor? Then what is Rs? Rs is equal to, you have to write this, relate this R A by L, cross multiply A by L. So we have to measure what is the length of the conductor. To remove this conductor, find the length by this scale, correct length. And diameter of the conductor. We are finding out, okay, you can find out the diameter of the wire by the instrument is known as screw gauge. Screw gauge is available. Diameter. So with this diameter, what is that? I want to calculate what is the area of cross section of the metallic wire. As you know, area of the cross section of the, what is that, circular. Circular shape cross section is pi r square, the metallic wire. Area of cross section of metallic wire is pi r square. R is the radius of the wire. That is radius of the wire. So write this R in terms of diameter. What is R? D by 2. D is written, what is that, measured. R is equal to D by 2. If R square means D square by 4. So area of cross section of the conductor is pi D square by 4. So write what is A? Pi D square by 4 L. Look at the final equation. Specific resistance of this conductor is calculated using the value what we have measured or determined from the Wheatstone bits R, and A, it is by, that is by D, diameter and length we have measured. Substitute them and find you get Rs, specific resistance of the conductor. So Rs, and also we can calculate the specific conductance. So resistance is, electrical restriction. Conductance is electrical flow, electric current, easy of flow, is it not? So specific conductance is inverse of this. So if you know the specific conductance of the substance, specific conductance of the material, we can able to mark it as, what is that, what kind of material is in terms of conductance. Is it a semiconductor? Because it depends on the conductance, higher conductance. Is it a good conductor or very good conductor? Is it a bad conductor or very bad conductor? Like that. So depending on what is the value of specific conductance, lower value, here a bad conductor, semiconductor. As the value goes up, conductor, good conductor, very good conductor. So we can grade that. What is that? We can classify those material as, what is that? What kind of the material conductor is a good conductor or bad conductor? what degree the conductance there. So that is the application of a V-stone bridge. So it finds out any material you can take. You can find out what the material is, what kind of the material in terms of conductance. That is the one. And using the same principle, we can also find out what is that the inductance because it has the properties of the conductors. Inductance, impedance, capacitance. I don't want to go in detail using the same principle. What is that? You can able to find out impedance of the conductor, that is inductance of the conductor, and capacitance of the conductor, like this. Yeah, so many applications using V-stone bridge. And this is about the physics. Physics means we take a solid material for that and find the properties or evaluate the properties, physical properties, parameters. In chemistry also it finds application. Chemistry means we take liquid. Here solid. In chemistry we take liquid. What liquid? Electrolytic solution. What is electrolytic solution? A solution or solvent in which what is that? The substance dissolved dissociate into ions, produce ions. A conductor. Electrolytic solution is a conductor. Where we are using electrolytic solution is connected. But one thing, if you connect directly into a solution, the current will not flow through the solution. We need a special electrodes. The electrodes, what is that? Platinum electrodes, through which what is that connected. So use what is that? The cell, that is special type of cell is made as conductivity cell with two platinum electrodes. Only between the electrodes what is that? Conductance take place. That is the conductivity cell is dipped and is connected here. In the same procedure, we are measuring the resistance of the solution. That is resistance of the solution. This is one resistance of the solution. And this stands for resistance. If you know the resistance, that is L by A here, in the solution what you take now? Length of the conductor, that is length of the solution enclosed between the two electrodes. A stands for area of cross section of the solution enclosed between the two electrodes. So it is taken as what is that? These electrodes are fixed in a cell. It is taken as cell constant, that is L by A. So the cell constant with this what is that? Directly we can write resistance and specific resistance of the solution. Like this same way, for the solution we are measuring specific conductance. For the solution we can able to measure lot of applications in chemistry this one, because this specific conductance of electrolytes is related to number of parameters, that is equivalent conductance of the electrolyte. What is meant by equivalent conductance of electrolyte? It is the conductance of an entire solution containing one equivalent of salt, one equivalent of electrolyte. That is important parameter. We can able to what is that? Determine. If you know specific conductance of conductor, it can be evaluated. If equivalent conductance of electrolyte is evaluated, we can find the degree of dissociation of that electrolyte. That is formula is there. Degree of dissociation means how much or what percentage of molecules are dissociated. When you dissolve a salt in solution, don't think that all the salts, all the molecules are dissociated. Only some molecules are dissociated, remaining molecules are in the molecular state. In some cases, it is 20% dissociation, 20% dissociated weak electrolyte. In some cases, 60%, 80%, 90%, 95% dissociated strong electrolytes. So we can able to find out degree of dissociation of electrolyte. Says what amount what percentage, what would be the kind of electrolyte, strong electrolyte or weak electrolyte, depending on the degree of dissociation. That is one more evaluation. And another evaluation, solubility of the electrolyte. How much of the salt is able to dissolve in the solvent. Solvent may be water or some other organic reagent or inorganic salt, organic salt, some other. So how much it is soluble, that is called solubility, because the specific conductance is related to all these parameters. If you measure the specific conductance resolution, we can evaluate using mathematical formula equivalent conductance, degree of dissociation and solubility of a salt. Many applications in chemistry. So we have this principle, that is this Wheatstone bridge applications, not only in physics, chemistry and also in other various fields where the resistance measurement is related to other parameters. So with this we have completed the chapter.